Jonathan mentioned zombies, so let me try and one-up Jonathan's uncanny valley with our self-replicating frog bots, which I'm going to talk about today. Like Daniela, I've worked in the space of co-design and sim-to-real for over 20 years now. In work with my colleagues and students over the years, we've created search methods that search over the space of all possible robot bodies, searching for those robot bodies that facilitate embodied intelligence rather than obstruct it. What do I mean by that? I agree with Mitten and some of the other speakers. It's very difficult to come up with the definition of embodied intelligence. Most times we're looking for a robot body that is able to exhibit useful, interesting, and safe behavior with a relatively simple neural control policy. We've done this with rigid robots in past years, as you see in the top row. In recent years, we focused on co-design and sim-to-real for soft robotics. As you see in the middle row in the bottom left, and in the bottom right, we've started to apply this to metamaterials. But I'm going to talk today about our attempts to adapt sim-to-real and co-design for biological robots. What you see in the bottom row are simulated soft robots evolved and optimized in simulation. And then we create physical copies of those soft robots using frog cells taken from frog embryo to produce the millimeter-sized Xenobots. Where does the embodied intelligence come in? It comes in several places. What you're looking at here is a single Xenobot. We're looking down through the microscope at the Xenobot. It is exhibiting embodied intelligence in the fact that it is moving and doing something in the dish. It has no neural control whatsoever. There is calcium signaling and other kinds of signaling between the frog cells that make up the Xenobot. And in this particular case, we would argue that this Xenobot is exhibiting a particular form of embodied intelligence, which is replication. One way to obviously be intelligent is to perform actions now in the present that ensure your survival into the future. Arguably, a more intelligent thing to do is to realize that organisms and machines, no matter how sophisticated they are always going to have a limited time span. Someone just mentioned self-driving cars that break down. One of the smarter things you can do is not just take actions that ensure your survival indefinitely, which is impossible, but ensure the survival of your offspring or copies of yourself that are likely to survive further into the future. And smarter still, ensure that those offspring produce offspring that in turn ensure the survival of their offspring. So in this study, we looked at self-replication as a particular form and possibly an extreme form of embodied intelligence. The human species, for better or for worse, we are having a hard time at dealing with creating a world that is safe and ensures survival for our offspring and their offspring. Back to the Xenobots. What are you looking at here? You're looking at a single Xenobot, which has been placed in a dish, and in that petri dish are dissociated frog skin cells. And through the action of this Xenobot, it is pushing some of these cells into a pile. If this pile is large enough, it contains more than 50 cells. After about 5 days, it will grow cilia. These are small hairs on the outside surface of this mass of cells. And after about 5 days, this clump, this light-colored clump that you see here, if left to its own devices, it will start moving, and you have a child Xenobot. This video, it was taken about 24 hours later. It's the same Xenobot, and you can see it's making this child Xenobot that's almost as big, if not bigger, than the parent. Where does the co-design come in here? It turns out that Xenobots left to their own devices will self-replicate, but they're very, very bad at it. They will produce children that do not produce any offspring. So we brought in co-design to see whether we could design a swarm of Xenobots, which you see in purple here. And the fitness of any given Xenobot swarm is how many generations of replication it's able to trigger. What you're watching here is an initial swarm at the beginning of an evolutionary algorithm. This is at the outset. You'll notice in this case, in this particular swarm, all of the 9 parents have a spherical shape, and you can see just through self-displacement, through motility and random action, they move some of these simulated individual cells into piles, but none of the members of this swarm make a pile that's big enough to mature into a self-motile or moving child. One of these piles is 74% of the way to a size large enough to produce motility. So the fitness of this swarm as a whole is 0.74. It was 74% of the way to producing a viable child. In this evolutionary algorithm, at a next generation, through mutation of the shape of the swarm, this new swarm, which has this donut shape, for whatever reason, based on the soft and compliant properties of this donut shape, the swarm of 9 original parents, as you can see here, they create a single pile which is large enough. That pile is in the top left there. That pile is large enough to become mobile, and it produces another pile that is 51% of the way to producing a grandchild Xenobot. This particular swarm gets a fitness of 1.51, 1 point for replicating, and 0.51 for producing a pile that's 51% of the way to replicating again. If we repeat this evolutionary algorithm for many, many generations, the evolutionary algorithm often converges on Pac-Man-shaped parents, like you see here. And in this case, these 9 Pac-Men produce 3 children, and one of these 3 children produces 1 grandchild. In essence, what the Codesign and the evolutionary algorithm is doing here is designing a Xenobot swarm that postpones the loss of replicative ability. What I just walked you through was one run of the evolutionary algorithm. Here are the end results of 99 other runs. You can see there's some convergent evolution here. It often converges on this Pac-Man shape, which makes sense. If you tend to move in a corkscrew, then having a leading edge with a concavity makes you act as a moving shovel, and it increases your chance of replicating yourself or your strategy into the future. Of course, if we're interested in embodied intelligence, replication on its own is not really of interest. So going back to the 1960s, John von Neumann proposed a theoretical construct that's capable of self-replication, which became the von Neumann machine, or the von Neumann universal constructor. A tells C to make a copy of A, B, C, and D. B copies the instructions here, phi, into the new machine. And D here is something else. So as the machine replicates, as A, B, and C replicates, D does something useful as a side effect. For von Neumann, that was self-replicating robot colonies that could colonize the solar system and beyond. We explored this idea with our self-replicating Xenobots only in simulation, where we designed a task D for them to perform as a side effect of the self-replicative process, which is to assemble soft, flexible circuitry. So the blue that you see here are flexible wires. They are adhesive wires. If the Xenobots move and they connect a battery to a flexible adhesive wire, and that flexible adhesive wire attaches to a very small light source, it closes the circuit, and the swarm as a whole turns on a light. In this case, you're watching a swarm turning on 2 of 4 possible lights in the upper left and upright corner. If we take that swarm, which successfully turned on 2 lights, we break the children into 2 groups. We place those 2 groups of children into 2 new partially constructed circuits. We can ask whether those 2 new swarms close the circuits in B or C. If we do and they replicate, we keep moving them from partially constructed circuit to partially constructed circuit, and we get more and more swarms that replicate and fix or assemble more and more circuits. This is in D here, what I'm showing you is this branching structure. Every red line segment here is a swarm closing a circuit. Every gray line segment here is a swarm that fails to close a circuit. That branch of the tree dies off. If we plot the number of completed circuits over time, we get exponential utility. We get more and more self-replicating machines that are doing more and more useful work as a side effect. I think I will leave things there, and happy to take any questions during the panel discussion. Thank you very much.